Hello and welcome to another video. In this video we're going to be going over all the problems from Weekly Contest 398. And this is probably one of the easier contests by far I've seen recently, so let's get into it. By the way, a little small trick you can do is if you actually go to the contest, if you're not solving it in real time, if you're solving after, what you can do is you can actually look at like how long it took people to finish. So if you go here, you can see like, okay, well, this guy finished like all the problems and like very, very fast. And question 4, most people finish very, very fast. So that leads me to believe that the last question is not going to be like super hard. Because the hard questions, like usually what happens is if the last question is very hard, usually this is around 20 minutes or 30 minutes or something. So it means that like this is one of the easier contests if the number one time is like 8-10 minutes or something like that. So just a small thing there, you can look at the difficulty and it's pretty accurate for the most part. Okay, so in the first one, it's pretty easy. Basically, they tell you an array is special if every pair of adjacent elements contains two numbers with different parity. And parity just means odd and even. So essentially, numbers have to alternate between odd and even. So here there's only one, so it's true, and here it's true, and here it's false because these two are the same. So it's pretty easy. You just go through your array, you compare every two numbers next to each other, and you just check, are they odd or even? And they have to be the same, or they have to be different, right? So you can just take every set of numbers right next to each other, mod them by 2, and if you get the same thing, then pretty easy. You just return false. Okay. So in the second one, you're basically doing the same thing, but now you have queries. So you can have 10 to the 5th queries and 10 to the 5th numbers. And you want to be able to answer these queries in O1, and you should be able to recognize that because you have 10 to the 5th numbers, or like in a logarithmic time, otherwise it won't pass. So you can't just say like, for every query, let me actually go through the whole thing manually and figure it out. So for this one, the thing you have to recognize is, in order for something to fail, there only has to be one failing case, right? So in this whole thing, if there's only one set of numbers that have the same, like that are odd or even next to each other, then this whole query fails. So in this case, there are none. Actually, let's see. These are the same, so it should fail. And then in this case, so 0 to 2 should fail because these are the same. And then 2 to 3 should succeed because these are not. So the main thing you have to recognize is how to do this. So if you're trying to figure out a query, typically, and this is a common pattern, if you're trying to figure out a query of like x to y, you can typically do 0 to x or x minus 1, and then you can do 0 to y, and then you can use that information. So you could do like, let me do all the stuff before this, and then let me do all the stuff up to this, and then figure out the difference, and then the difference will give you some information. So that's kind of what we can do here. So essentially, we can just maintain a count of how many failure cases there are. So we maintain a count of how many failure cases there are. And then if we have a query, so for example, for this one, if it starts with 0, there's not much to do. But basically we just say, okay, well, if the count here, so actually in the query, so I guess in the query 0 to 4, basically what you would do is you would say like, what's the count in this? And you can do that in a hash map. So you basically just maintain like a prefix count of like how many failure cases are there up until some index. So for 0 to 4, we can just check like how many failure cases are there up until 4, and we would see that it would fail because there would be one failure case. So we can even print, we can print count here. So that's basically all I did is just make a dictionary. And then you could say like, oh, look, at this index, there's a failure. So that means there's one failure case. Okay. And then for the second example, so 0 to 2, same thing. You would just print, like, what is it? So you can check, oh, at 2, there's a failure case. Okay. What about 2 to 3? So 2 to 3 is this range here. So then first I'm going to check how many failure cases are there before this, which is up to here. So in this, I'm just going to check what's my failure case from 0 to x. And then I'm going to check from 0 to y. And if 0 to y has more, that means that in x to y, there are some failure cases. And if there's only one failure case, it fails. So basically, these have to give you the same exact thing for both of these. So if we go back and look over here, for 0 to 2, it obviously fails. But then for 2 to 3, we check, okay, what's 0 to 2? 0 to 2, there's one failure case. And then 0 to 3, there's also one failure case, which means the failure case had to be before this query. So that's the basic concept there, is you just maintain like a prefix count of how many failure cases there are, do 0 to x, and then do 0 to y, and then if they're the same, that means there's nothing in here that failed, it's all before. So also not too bad, pretty easy, I think. Okay. So this one is basically like a combinations problem, but it's like pretty basic combinations. So essentially, if you have a bunch of numbers like this, and you want to get all combinations of all of these numbers, there's kind of two ways to do it. All combinations of pairs, anyway. There's kind of two ways to do it. One, you can say, okay, for every one of these numbers, I can match it with everything else. So for example, with 1, I can say like, okay, let's do 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, right? But the problem with that is you'll get duplicates. So because when you do that with 2, you'll get 2, 1, 2, 3, and so you'll get 2, 1, which you already have, and then when you go to like 3, you'll get 3, 1, and so on. So basically, if you do it this way, if for every single number you match it with everything else, you'll get double the count. Or you could do it another way. You can say, if I have this, I'm just gonna, for every number I have, I will match it with every previous number, and that will avoid duplicates. So for 1, I have nothing, but for 2, I'll match it with 1. For 3, I'll match it with 1. For 3, I'll match it with 2. 4, 1, 4, 2, 4, 3, and so on and so on and so on. So that's kind of the way that I did it, and that will give you every pair, essentially, with no duplicates. Or you could do it the other way. But the idea, basically, is for every single number, we can just... So let's kind of walk through this. So let's say we have, like, this example here. So basically what we'll do is we'll just store the digit... the digit we're on, like, is it the ones digit, the tens digit, the whatever digit, and then how many total count of that digit are there, and then how many numbers did we go through. So for example, for 13, we'll store the 3, and we'll say that's at location 0. So at location 0, we have 1, 3, right? So we have 1, 3. And how many total numbers did we get so far? Well, we got none, so there's nothing to do there. There's only 1 and 1, so there's no differences there. Okay, and then at location 1, right, the tens place, we'll have 1, 1. Now for 23, we'll say, okay, well now we have 2 3s at here, and we also have 2 total numbers, so there's no differences here. And then at this location, we have 1, 1, but we also now have 1, 2. So because we have a 2, we're basically going to say the number of differences is the number of 2, like the number of 2s we have, right, minus everything else. Or it's actually not going to be the number of 2s we have minus everything else. It's going to be it's not going to be the number of 2s we have minus everything else. It's basically going to be the total number of numbers we have minus all the numbers that aren't 2s. So in this case, we have 2 numbers total, right? We have 1 of each, and there's 1 number that's not a 2. So that's 1 difference here. And then for 12, once again, so we'll say for 12, the 0 place is 2. So we'll have 1, 2. And here we have 1, 2, but we have 3 whole numbers. So there's 2 differences because that 2 is different from the 2 3s. So we have 2 more differences. And then we also have a 1 in the ones place, which is 2 1s now. So we do the same thing. We say, how many total numbers do we have? We have 3 minus the number of 1s, because whatever number you put in is going to be different from all the other numbers that are in there, right? So if you have like the basic idea is like if I have this and I put in a 1, then how many numbers is this 1 different from? Well, the answer is just going to be the total number of numbers, which is 5 minus the number of 1s. So that's kind of the idea. For every digit, you just keep storing the count, and then you just check how many total numbers do I have so far, and then how many numbers are there that aren't this number, and you just have a basic dictionary and like a length to do all that. So pretty straightforward, and basically, yeah, you just... So I definitely think like if you are doing these contests, I think these first 3 problems you should be pretty happy if you get the first 3 problems, but consistently. Like, I'd say for the last, I want to say 10 or so roughly contests, I was able to get the first 3 pretty quickly. Like, I don't remember the last time a third problem was too hard. So these first 3 should be like bang, 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 done. Like, if you're pretty good at this stuff. And ideally, you should be able to do the first problem like in a couple minutes, second problem in 10 minutes or less, and then third problem maybe 25 minutes or less. But yeah, so that's kind of the basic idea. You just do this, and it's pretty easy. And then if you have any more questions, like in deep, like if you want some clarification or something, you can ask in the comments. Okay, let's go to the last one. So the last one's actually not that bad either, because the constraints are really easy. So you can actually just do a basic DP, but let's look at it. So we have a non-negative integer k, and there exists a staircase with infinite number of stairs with its lower stair numbered 0. Alice has an integer jump with initial value 0. So essentially you start, so if there's some stairs like 0, 1, 2, 3, so k, you start over here, and you're trying to get to k. But even once you get to k, you can still like not be done. Like you can like go to k and then like go back and go to k again, and they'll kind of show you this. But essentially you have 2 choices. You can either go back 1 stair, you can't do this twice in a row, and you can't go back from 0, or you can go up from your stair to stair I plus 2 to the jump. And jump starts at 0. So at first you jump 1 stair, then you would jump like 2 stairs and so on. And that's what makes this problem kind of easy with constraints, is essentially, if you think about it, even though this k is really big, is 10 to the 9th, you're basically jumping like 2 to the 1, 2 to the 2, 2 to the 3. And so I think it's like 2 to the 40 or something, which is like 10 to the 9th. So essentially, once you jump forward like 40 times or so, maybe 41 or something, you're basically done. Like, all the jumps after that will be like 10 to the 9th, because it'll be like your jumps are going to be like 2 to the 40th. So that's why the constraints are really easy, because you're not just going to go like from 0 to 1 to 2 to 3. You're going to go from like 0 to 1 to 3 to 7 to like 15 to, you know, whatever, 20 something and so on. So you're going to be jumping like really far forward. So the constraints are actually, just because the number is big, the constraints are actually really small. And so anyway, so essentially, yeah, when you jump, then your jump increases, and you want to return the total number of ways you can get to k. And they tell you you can get to k and then perform some operations to get to k again. So let's take a look. So here, k is actually 0. So we start at 1, and we want to get to 0. So one thing you can do is you can go back. And remember, if you go back, you can't go back twice in a row, and you can't go back from 0. So you can't go to -1. Or you could go back. So you would go back to 0, and then you would go forward 2 to the 0 times. So you'd go forward to 1, and then you would go back again to 0. So those are the 2 ways. Now, the second example is k equals 1, and this gets even kind of funkier. You start at 1, but you see there's still 4 ways to get to 1, even if you started. So 1 just says you're done. Another one is you go down, then back up. And then let's see. Or maybe there's 3? No. So you can also go up and then down, right? So you can go down and then back up. You can go up and then down. And then you can also go down. Then you can go back up. Then you can go back down. So it'd be like, so you go down here. Then you jump 1. Then you go down. Then you would jump 2. And then you go down again. So that's the last one. So basically, you can come up with all these things in DP. And like I said, even though this index is technically 10 to the 9th, you're going to be jumping, like you're not going to be covering too many indices, because you can't go back more than once in a row. So the number of combinations isn't that many, and you're going forward a lot. So that's kind of the idea, is even though the I is really big, you're visiting like 50 states or something. You can like maybe write it down, but yeah, if you write like 10 to the 9th or something, you're not going like 1 to 2 to 3 to 4 and so on. You're skipping most of them. So then the only information you need is, what stair am I on? Can I go back? Which is a Boolean, which costs you basically nothing. And then how many jumps do I have? And like I said, this jump will only go up to like 40, because with 40 you basically jump from the 0 to 2 to to 10 to the 9th in one jump. So the first case we have is the case where we can never make it back So if k is like, let's say k is 1 here. So if we're at 2, we can get back to k, but if we're at like 3, we can't get back to k because we will go back 1, then we have to go forward, then we can go back 1 again, then we have to go forward, and so on. And your forward jumps are going to be bigger than 1, and you're only going back 1. So if you're at greater than k plus 1, you can't get to k anymore. Also, you might start at k, and so here you basically just initialize your result to either 1 if you start at k or 0 if you didn't. Because for example, in most of these, like let's say we can start at here, like that's already one way to do it, just do nothing. Then it's pretty straightforward. So we just check, can we go back? So if we can go back, we just add that state, which is just I minus 1. Then we can't go back anymore, and our jump stays the same. And then the other state is just go forward by 2 to the jump. I mean, we can even do like this, I guess. I don't think it matters. So, but because like I said, there's only like 40. If the problem where jump would be like 10 to the 5th or something, then you'd want to like pre-compute and cache this stuff. But because it's only like 2 to the 40, it doesn't really matter. You don't need to do all that. So you can just do it this way. So essentially, we can always go forward, and we might sometimes go forward too far and then be out of bounds and so on, but we can always go forward and at least try. And we can't always go back. So essentially, if we go forward, we just go 2 to the jump, and then we can go back. So our state of going back after that is true, and then our next jump is just jumpless 1. And your initial state is just index 1. You can go back, and your initial jump, like 2 to the whatever, is just 0. So actually not very hard, like closer to a medium, maybe an easier hard. So that's what I'm saying. This contest is like easily doable compared to the rest. Usually I'd say for maybe half or a third of the problems, this last problem is insane. Like most 7-star difficulty problems or 8-star difficulty problems are pretty insane and are probably not doable in interviews. Like I'd say, in fact, are not, unless you're like a pretty good competitive programmer. So, yeah. But this one is definitely like this. Like honestly, this can be an interview question. I don't think it's very hard. Yeah. So let's go through the time and space for all these really quick. So like I said, even though you might think this technically like I times 2 times jump, which, like I said, is like, you know, log of 10 to the 9th or something. This I, you're skipping most of the cases, so that's why it passes. And space, same thing. So something like this, but like I said, it's significantly less than that. And obviously we can get rid of this guy. So it'd be something like this. So instead of, I guess, log k would be better. Like, so I guess this would be like k, 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 something like this. And even though it looks like it will fail, because you're skipping that, it passes. You're skipping most. Let's see. This one, you're basically going through every number and you're doing bit by bit. So that's just like O of n. And then because the numbers are pretty small, yeah, so the numbers are only 10 to the 9th. Like you only have 9 digits for a number, so I'd say that's like constant time. And then space is O of... So for every single index, you'll have a bunch of numbers, but your numbers can only be... Your numbers can only be 1 to 10, so it's O of n anyway. Right, because like at some index, like let's say the 0th digit can only be 0 to 9. So if I was doing this in Java, maybe I'd use an array here instead of dictionaries. Like maybe I'd have like a nested array or something, where I'd have like, yeah, like an index and then the letter counts or something. You can make an array there instead of a dictionary. All right. So for these, so this is O of n as well. Oh, so this is actually, so it's O of n to build the thing, and then O of like q to get the queries. So you can get the queries in O of 1, just because you have the counts, and then space. So you did build like this count, so that's O of n. Last one is just O of n time and O of 1 space. So yeah, I'd say if you want to know like where you want to be, kind of, if you're doing very well, at least for me, like I think where I'm at right now, is I can probably do, like on a good day, I can do the first 3 problems, all of them in under 30 minutes combined. I think that's a pretty decent goal, and it's definitely doable. Sometimes I can do them significantly under 30 minutes. Like it usually depends on the third problem, like how hard it is. First problem is usually like 2 minutes. Second problem's under 10 minutes, and then third problem varies in difficulty. Sometimes it's closer to a hard, and then this last one very varies on the difficulty. Like this one I was able to do pretty quickly, but then there's the crazy ones I either can't do it or I can't do it. I have to look at a solution and then I have to code it, and sometimes it still takes me like an hour or two. Sometimes I can figure it out and it'll take me like an hour. It just like those strongly depend on the difficulty, because you can imagine like the problem with LeetCode is there's only easy, medium, hard, where in reality, if you give a problem a rating 0 to 10, let's say like 0 to 1 is like an easy, 2 to 4 or something is a medium, and then like 5 to 10 is a hard. So this range like varies insanely. So like there's hards that are closer to a medium, and then there's hards that even if you know how to do it take hours, which makes sense, right? Because there's nothing harder than a hard, so it's like you can't market anything else. So if you put some like insane problem that no one could solve, like what else would you give other than a hard, right? So that's why it's not the best. Maybe they can like use a rating or something instead, like on like code forces or some other stuff. Probably be a lot better. I guess they kind of do on the contest where they give it 6, 7, and 8, but even then, I don't know how accurate that is. There's some like 7-star problems that are like there's some 6-star problems that are hard, so I don't know. But yeah, it's going to be all for this one. If you did like it, please like the video, and please subscribe to the channel, and I'll see you in the next one. Thanks for watching.